When we think of chemistry, perhaps the iconic image that comes to mind is that of the periodic table. But before we can talk about the history of the periodic table and why it is arranged the way it is, we first have to talk about atoms and the development of the atomic theory. To do this, we actually go back several millennia to the early Greek philosophers in the 3rd and 4th centuries BC. A major philosopher during this time was Democritus. And during that time, philosophers really were the early form of scientists. They explained the observations of the world that they saw around them, as well as that of the human condition. And Democritus had proposed that all matter was composed of extraordinarily small particles, which he termed atomos. And that's actually where we get the term atom today. And he had proposed this in the early 3rd and 4th centuries BC, but very little progress occurred in atomic theory over the next 1,000 years. And that is primarily due to the fact that a more well-known philosopher who came after Democritus, Aristotle, did not believe in infinitely small particles. He believed that all matter was infinitely divisible, that there were no fundamental particles. And Aristotle's ideas dominated Western civilization for the next 1,000 years. And as a result, there was very little progress in this idea of atoms. And all of that kind of happened until, honestly, up until the very early 1800s, when an English school teacher, John Dalton, looked at some of the observations that had been made in the world around him. Science had started to make much more progress in the 15, 16, and 1700s. And he looked at some of those observations and returned to Democritus's proposal of atoms, and then took that and formulated it into a theory that was kind of cohesive by 4 main postulates. This was all proposed in the time period around 1803 to 1807. And his 4 postulates really cemented this idea of atomic theory in a more complete way. His first postulate was that each element is composed of extremely small particles called atoms. That's essentially just repeating Democritus's idea. Now, elements that have been discovered at this point would have been things like gold, copper, iron. And scientists knew that there were differences between these elements. And so John Dalton proposed that each of these elements were composed of essentially atoms. And here shown in red and blue is simply an atom, a cartoon description of an atom of the element oxygen versus an atom of the element nitrogen. Now, the second postulate is that all of the atoms in a given element, such as copper or gold, were identical to each other. But atoms of one element were not identical to atoms of all of the other elements. So atoms of the gold element were different from atoms of the copper element. Atoms of the oxygen element were different from the atoms of the nitrogen element. Additionally, he formulated this proposal that atoms of one element cannot be changed into atoms of a different element by normal chemical reactions. And additionally, that atoms are neither created nor destroyed in chemical reactions, that there is no way to just form a new atom or destroy an atom during normal chemical reactions. And his fourth postulate is that compounds form when atoms of more than one element combine with each other, and that a given compound always has the exact same relative number and kind of atoms. So the compound NO always contains 1 nitrogen atom and 1 oxygen atom. Now, some of these postulates might seem a little strange to you, or perhaps if you're familiar with this, you might think that some of these are obvious, but these were formulated specifically to both explain and predict some of the observations, explain the observations that Dalton had already seen in the world around him. So his theory explained a couple laws that scientists had already formulated. The first is the law of conservation of mass. Scientists had already noted that the total mass of a reaction beforehand and after always matched if you were very careful to account for for possibilities such as the formation of a gas and collect that gas. If you collected all of the mass both before and after a reaction, those masses always matched. And Dalton's theory explains this now, because if matter is composed of atoms and atoms cannot be created or destroyed, then the total mass must remain the same. Additionally, Dalton's law explained another law which had been discovered previously, which is the law of constant composition. This simply says that in a given compound, the relative numbers and kinds of atoms are constant. So in the compound N, in that NO compound example, you always have one nitrogen and one oxygen atom. In water, which is composed of 2 hydrogen atoms and 1 oxygen atom, it doesn't matter where you sample the water from, whether you got water from the top of Mount Everest or from the Marianas Trench or anywhere in between. That water is always at a fundamental level composed of 2 hydrogen atoms and 1 oxygen atom. And that's explained again by Dalton's postulates. But his postulates also serve as a predictive tool. So they predicted some laws. One, which is known as the law of multiple proportions. And this law states that if 2 elements, A and B, combine to form more than one compound, the masses of B that combine with a given mass of A are in the ratio of small whole numbers. This might seem like a bit of a mouthful. What exactly is this saying? Well, let's take an example. So what does this mean? Let's compare water, H2O, versus hydrogen peroxide, H2O2. Now, these are the 2 elements, A and B, hydrogen and oxygen. And they can combine in different ways to form more than one compound. So they combine in one way to form water, combine in a different way to form hydrogen peroxide. And if we take if we hold the mass of one of those compounds constant, so 1 gram of hydrogen will combine with 8 grams of oxygen to form water. If we hold the mass of hydrogen constant, that same mass of hydrogen will combine with 16 grams of oxygen to form hydrogen peroxide. And so the ratio of if hydrogen is the A element, the ratio of the B elements to each other end up being 1 to 2 here in terms of their masses. That is what this law is essentially explaining. So if we have 2 elements that come together to form multiple different compounds, and so if we had hypothetical compounds that was AB and then AB2 and AB3, if we held the mass of A constant, then the ratio of the B masses is going to, for each compound, is going to be a small whole number.